Hello, welcome back. We are talking about artificial neural networks, how they are constructed and how they learn. In the first video of this series, we saw how they are built. In the second, we talked about how to program one by hand. Now, one thing we didn't talk about are multiple layers. Normally, you don't have a neural network consisting of only one perceptron, right? This would be a little silly because it cannot do much. It can just calculate an AND or an OR, which is not very much. Normally, you get the effects of the intelligent function of the neuron and of the learning function of the neuron when you start connecting more of them together, perhaps hundreds, perhaps thousands, but there is not necessarily much point in connecting them all on one layer, because how many you connect to one in one layer depends on how many inputs you have. You remember that the neuron, if you look at it, let me show it to you. If you look at it like this, every input is connected to an actual input. So let's say I have a logical input, then I have, two inputs to my neuron because I want to have the two input values. Now, if this was a neuron that processes an image, then I would have an input for every pixel of my image, right? So if I have a, let's say, I don't know, 100 by 100 pixels small video feed that my robot is looking at, then I would have 100 by 100, 10,000 input values, one for each pixel. But then, my inputs are exhausted. I cannot do more processing. How do I do more processing? By connecting these neurons in layers. So after this neuron, we said already, the output will branch at the terminal branches in the biological neuron and will go to other neurons and then to other neurons and so on. And so I end up having something like this here, where I have these different layers. So here this is rotated a little, so the input is at the bottom and the output is at the top, but it's the same thing again. I have two inputs. I have three neurons in the first layer, I have one neuron in the second layer, and then I have an output. And this now is a little bit more complicated neuron. It can do more things, because now it can not only sum up a number of inputs and then produce one output, but it can now first sum up the inputs differently and create different outputs. And then in the second layer, you have another neuron taking these already processed inputs as the output of the previous layer and doing some further processing and perhaps combining them in interesting ways, taking, for example, the outputs of the first and the third neuron, multiplying them with a high synaptic weight so that these are important, and silencing the middle neuron by multiplying it with something less. And so now you get a really interesting behaviors where, if you think of it in terms of mathematical functions, you can have a function that is very complex and not linear at all. And the more layers you add, the more complexity you add, the more non-linear, the more folded your function can be that you are modeling, the more complicated the information is that you can store in this network. The more different behaviors it can show at the output, the more complex behaviors it can show, the more complex. If you think of it of mathematical function, it is essentially a function, right? A neural network is a function that has as its inputs, its domain, the input values that you put in it, and as an output, it has the function value, whatever comes out of the function. So the whole thing is actually a function. And how many layers you have tells you how complex this function can be. Is it a linear function? Is it a quadratic function? Is it a cubic function? Or is it even a much more complex function that can map really complicated inputs to really complicated output behaviors? And this is something we need in real life, right? To give you another example of something like this, one example is, of course, face recognition. When you look at your phone, then your phone will take your face, divide it into pixels, send them as inputs to neural network, and then you have multiple layers, right, where the signal goes through and the synaptic weights are made in such a way that in the end it recognizes you, it is trained. How the training works, we will talk about later, don't worry about this now. And at the end, let's say you have 5 different users who are recognized. So ideally, you would have only 5 neurons at the end, at the output. And when each one fires, it represents one user being recognized. This is a very typical way of encoding these things in neural networks. You have one output for everything you want to recognize. And how strong the output is gives you the confidence that this thing was recognized. So if it's my face, let's say Andy, and my neuron is this one, so the second finger here, when this fires, my index finger, then I have recognized an Andy, right? And the other is, Peter and Mary and John and whoever else. So at the end, when this neural network fires, and it recognizes Andy, then perhaps the Andy output will be 0.8, while the others will all be less than 0.5. And then I have some confidence that actually Andy was recognized. If Andy is 0.9, then my confidence is higher. Andy was recognized even better. And if the others are lower. While, for example, let's say Andy and Peter look a little similar, then perhaps these two will both be at 0.8 and the others be at 0.1. So I know it's either Andy or Peter, but I'm not sure which one. Because perhaps the light was bad, perhaps Andy didn't wear his glasses and Peter also doesn't wear glasses, and so the network was confused. So this is how this works when we use these networks to actually recognize something. Now, the important thing to realize is that whatever the neural network does, whatever the perceptron can do, this whole knowledge that it represents, right? Because if you think back to this neuron we had, which does the logical, here we are, that does the logical function calculation. If you think of this thing, then whatever this does is encoded where? Where is actually the knowledge of this? Whether it is, let's say, an or an and logically. Where is this encoded? It's encoded in the weights and in the threshold. That's all. There is no other point at this thing where you can store anything. So the weights and the threshold are the points at which this neuron can accept any kind of customization, any form of information. The rest is fixed. It will multiply, it will add up, it will compare with the threshold. So the whole information that I can give this neuron are the synaptic weights and the threshold. And this means if you think of neural networks that actually do something useful, like the one in your brain, it means all the information in your brain is stored in the synaptic weights. All the information in ChatGPT or in the Facebook face recognition is stored in synaptic weights. The synaptic weights are where the information is stored in a neural network. There is no other place. There is no memory it has access to. Everything is in the synaptic weights. Your brain is essentially, self-contained in this skull of yours. There is no external memory anywhere, right? Whatever you know, all the language you know, all the languages you perhaps know, all the people you know, all the memories of the past, all your knowledge of what you have been studying, for example, about neural networks, is all somewhere in your synapses. And this means, the more synapses I have, the more neurons I have, the more layers I have, the more information I can store. This is why you have 100 billion of them in your brain, because you need to store all that information that's in your brain. All the school stuff you learned from the first class of primary school until now, all the world history, all the physics, all the chemistry, all the mathematics, all is there. All the face recognition for the people you know, famous politicians, famous actors, your family, all these things are stored in your synaptic weights. Everything you know, everything you can do, your ability to do mathematics, to calculate physics, to calculate the molarity of a solution in chemistry, to remember how neurons are built, All these things have to fit there. All your knowledge of geography, where is your home, how do you get there, how do you get to the next town center, where is the shop that sells your favorite cookies. All these things have to be stored as synaptic weights. Now you understand why neural networks have to be so big, because every synaptic weight is just one factor, is just a tiny little nudge that will make an electric signal go through your brain in a particular way or in another way. And this will eventually make your brain perform this knowledge that is stored in it, that has been learned. Okay, so this is very important. Everything is stored in synaptic weights. So we want to have as many of those as possible. The more synaptic weights you have and the more layers you have, the more complex behaviors you can store. The more complex behaviors your network can exhibit also. Now, why don't we make huge neural networks then with billions and billions of weights? Then they could store everything. Yeah, right, they could. But the problem is that also every synaptic weight is one calculation. It's three calculations. It's first the multiplication, it's then the addition with the other synaptic weights, and it's a comparison with the threshold. And so the more of them I have, the more I have to calculate in every single step, because every input signal has to go through the whole network to arrive at the output. For example, if I have, like I said, this camera feed that recognizes me, then I have 10,000 input neurons, and every single synapse is a calculation, it's three calculations, and then I have the next layer, the next layer, the next layer, and at the end I have an output that says this is Andy. And this will take forever if I have billions of neurons. Our computers are not fast enough for this. This is why artificial neural networks don't usually have 100 billion neurons. They have, a much smaller amount. What your phone is doing to recognize your face, perhaps it has only 1,000 or 10,000 neurons. It doesn't have even 1,000,000, because this would be much more than your phone can actually process in real time. So this is the problem. These are costly. And because we need so many, we have to limit ourselves and we have to make smaller neural networks. And this is why we cannot build a brain, just putting 100 billion of those together and then you have a brain. Perhaps it would work, but we cannot put 100 billion of those together and execute them in real time so that we get a brain, right? We can only do it with much smaller networks. Okay, so the important thing here is to learn. You have multiple layers, and multiple layers are important because the more layers you have, the better you can perform. The more distinctions your network can make, the more complex the function curve is that it can model, the more complex behaviors it can have. But also, this is costly. The more neurons you have, the slower it will be. And the more also, of course, memory it will use in your computer, because every one synaptic weight takes up a byte of memory, right? You need to store it somewhere. And 1 byte is probably not enough. If you have floating point numbers, you need at least, 2 or 4 bytes for every synaptic weight. So this very quickly multiplies and becomes a very big number. And so this is what you need to remember in the end. How many layers you have is a balancing act. And there's an art to it, to think how to dimension your neural network, how many weights you really need for what you're going to do, and how many layers you need. And you always try to pick the minimum of that, right? So that you don't overload your computer. Okay, that's it. In the next video, we will now actually simulate this neuron, this perceptron, in a spreadsheet, which is a fun way to see what it is doing. And then we will also talk about how neurons actually learn. Thank you, and see you next time.